We will start with our course. We will be starting with the first set of lectures, which are titled History of Ideas on Mountains, Tectonics and Geodynamics, followed by a talk on plate tectonics and orogenic cycle, paradigm and debates, followed by lithosphere definitions and the Earth's topography. Before I hand over the mic to Oliver, I'll just give you a very small brief introduction about him. We've already heard in the inauguration ceremony that he comes from the CNRS lab, the Geoscience Environment Toulouse, which is based in Toulouse, France. But Oliver is primarily from Germany. He has a German background. He is a full professor at the Paul Sabatier University, which is based in Toulouse. And I think, if I'm not mistaken, he's the deputy director of JET. Not anymore, he's finished his term there, but he was the deputy director at the JET. He finished his PhD in 1997 from the University of Minnesota in USA. And his topic was the role of partial melting during late orogenic collapse. He's been working on several research topics which are related to structural geology, analysis of migmatites, geochronology on zircons and monazites, on several themes like the growth and differentiation of the Earth's continental crust, and etc., etc. So the details of that we will surely learn over the week. So I hand over the mic now to Oliver to start with his talks. Thank you so much.
Thank you, Malika, for this nice introduction. Can you hear me all, so I can avoid the microphone, so then I can move? No, I'm a tectonics, geodynamics person, so I need to move, and show things and be able to do motions. So that's the template for this week. And really what I want to share with you is my own thinking, but also put them into a context, a very large context in terms of history. I think this is something you need to do also as researchers, to try to understand where people were coming from. What was their historical concept, the mindset the people had at the time they did something. Because research is all about doing something different. You don't want to break everything and start from scratch. But if you want to do something different, you need to understand where people were coming from in order to identify what is robust and what needs to be improved. So this is what we will do this morning, and then we'll set up some kind of paradigm, but also identify questions about plate tectonics, orogenic cycle. And then we'll start with definitions. So that will be for this morning. Tomorrow morning I'll start the day with structural analysis of migmatites, which is really what is my main expertise, I think. And I started when I was even younger than you. I was a bachelor student, I was thrown in migmatite terrain of central France, and had no clue on how to deal with that. So I tried to develop an expertise that will help better understand what is the record of these rocks. And then we'll apply these ideas to the Alpine Himalayan belt and Tibet plateau. I think it's important to add Tibet to the picture. And that will keep us busy for tomorrow, Wednesday, Thursday. And we'll see different steps in the evolution of the Alpine Himalayan belt, with the Western Alps, Himalaya, Tibet, Aegean domain, and I'll develop that in the next few days. And then this will provide us thoughts and examples to nourish a thermal mechanical model for the evolution of Phanerozoic orogens from a stage of wedge mechanics to orogenic plateau and collapse of orogenic belts, relying on the mechanics, thermal evolution, and then combine both of them, thermal mechanical models. And then we'll see how this might apply to Precambrian cratons. As you guys we are here in India, and probably most of you are working on projects on India. Most of the Indian continent is made of Archean Proterozoic rocks, so I think it's compelling to you. And I'll open a gate here with how these thoughts on Phanerozoic origins might apply or not to Archean Proterozoic cratons. Okay? I hope we'll... So don't hesitate to raise your hand, ask questions. I'll ask you some questions as well, so do not hesitate to provide answers. There are no stupid questions, no stupid answers. I'll start right away. What drives Earth topography? How do mountains form? What is your first click in your mind when I say that?
Collision of plate tectonic plates. When they go like
Collision, plate collision, okay. And can you develop on that? Plate collision,
folding.
what happens? Folding, deformation.
Yes.
Deformation. Is this enough to generate topography? There are some underlying concepts. Isostasy. That's important. So we will see that actually plate convergence is so what you say, you know, when I ask the question for first year students, oh, mountains, it's like this. No, plate convergence is mostly like this. And then some isostatic rebound, right? So plate collision is like this, and then, right? So gravity is very important. And it's been, I think, forgotten for many years in tectonics and geodynamics. Okay, and what controls crustal differentiation? You know that the continental crust is made of an upper crust dominated by sediments, volcanic rocks, intruded by plutonic rocks, mostly granite, a middle crust made of metamorphic rocks, mica schist, gneisses, and then a lower crust made of granulites, mafic, and felsic granulites. And that's overlying ultramafic rocks, peridotites. Actually, I won't too much develop on that unless I decide that with our interaction is of interest to you. But I think this boundary, the MOHO, which is a geophysical boundary, is questionable in terms of its significance in terms of petrology. Now, I was in the field recently, and people would not agree where to put the MOHO in the field, where you had ultramafic rocks and mafic granulites, most of them. Mafic granulites, they're made of garnet, pyroxene, plagioclase. And their density is about the same as the one of ultramafic rocks. So the geophysical MOHO might be moving, you know, from mafic granulites to ultramafic rocks. This is a topic I'm not really sure I will develop on that, but that's something I think is something to be worked on in the next years. So what controls crustal differentiation? And growth and differentiation? Which geological processes you think might be involved in that? Mostly magmatic. Magmatic and metamorphic partial melting and melt segregation, migration, transfer, and at the place of magma emplacement, also segregation between crystals and melt. So what I proposed and developed this week is an integrated approach from lithosphere to mineral scale. So we'll deal with lithospheric plates, and we'll define that at the end of the morning. See how it behaves at the Earth scale, but then moves to structural analysis, and then link structural analysis to textures as the scale of minerals, and it's hard to read it here, but you have monazite, zircon, and you need to see where they are before you date them, and you analyze them, and in order to date them, it's important to understand their textures and textural position. You always get an age. If you do a laser ablation analysis of a zircon, well, you always get an age. You know? It will give you a uranium-lead isotopic ratios, and this will yield to an age. What is the significance of this date, actually, we should say, in terms of age, timing of a geological event? Is something very linked to your understanding of the textural analysis of the minerals and their textural position. If you don't do that job, you're not going to do crap. And even the best statistics is not going to help you. Statistics is going to help you to refine the age, but not to resolve the age. So let's start our historical journey. So we'll go from continental drift, which stipulated at the time from a meteorologist, interdisciplinary. Meteorologist, Wegener was a meteorologist. I think he looked at how the glacial, the polar, missed the word, ice caps behaved and how they moved, and that's probably gave him this idea. When he was doing research on the ice caps and was looking at ice breaking into pieces and then bringing it back to it, I think it probably gave him this idea. I'm not sure. But you can find his book. It's easy to find. It's a very interesting scientific adventure. And he said that continents made of aluminum silicates are drifting on top of the CIMA, the mantle. So we moved to plate tectonics in the 60s. That stipulated that what is moving is not only continents, but the lithosphere, crust-post lithospheric mantle, relative to the astronosphere, and we'll develop on that. We'll also look at the work of pioneers in geology, with Argan, a very creative geologist working on the Alps, and he reconstructed this tectonic evolution of the Alps, which was then reproduced in analog modeling, with a little bit of clay and sand and some kind of torque, which will produce that exact deformation. And at that time, what they gained from that is mountain form in response to horizontal shortening, deformation. And we'll move to float-up tectonics. So you see that cork, that is plunged into water, and then what he wants to do is go up. So not much of anything horizontal here, right? Mostly vertical. Mountain formed by accretion of slab decoupled buoyant units. This is a concept that we're going to develop this week. And then Saint-Nectaire tectonics. Saint-Nectaire, you probably don't know what it is. It's a cheese from central France, which inspired me a lot when I was doing my first field work in central France. And you see it's kind of soft and weak. Mountains flow under their own weight. Gravity. Gravity, again, to construct and to destruct mountains. And that, I think, is even more compelling. It's compelling to phanerozoic belts. We'll see that during the week. But it's also and even more compelling for Archean Proterozoic. Because the crust was weaker because the Earth was hotter. See, the reasoning is starting to build. So if we move back even further, in the 16th centuries, mining and geology started in Saxony. Really, mining started before, but at the time before, you just had to pick up the metals that were shining at the Earth's surface. But the understanding was needed after all the easy spots were discovered. Then geology came into play, and geology really developed together with mining, and that's the work of Agricola in Saxony, in Germany, nowadays Germany, with the Erzgebirge, which means metal-rich mountains. And they developed techniques to dig, to break the ore with fire, so they needed wood. And believe it or not, well, geology first developed with the analysis of veins, structural analysis, the cross-cutting relationships, because the ore were identified to be localized in veins. But then sustainable development was introduced right away by the guy that was responsible for one or two centuries later on of these mining activities. He said, if we continue like this, to break the ore with fires coming with wood, we will soon be out of wood. So we need to plant. We need to plant trees if we want to continue exploiting. Sustainable development didn't come the last 50 years. It was right away. We forgot it, and now we are reminded that it's very important. The first Earth model, I like this one, Descartes, 1644. The world was made of, at the time he thought, sky, transparent matter, sun and stars, luminous matter, and Earth, planets and comets, dark matter. And for some reason, he put an internal fire at the center. What was his mindset at the time? Where the idea comes from, this internal fire? Volcanoes, right? Volcanoes. So imagine that there's something burning inside to feed these magmas. Put yourself into people's mindset if you want to understand their models and what is robust and not robust. And then there was an internal crust, solid and heavy and contains metals. Well, they knew that was where they needed to go to find metals. That was overlain by an external crust made of stones, clays and sands. These are the sediments. And you see inside, in between these two crusts, there are water and air. This probably comes from cave exploration. You know, they could tell that if you go inside the earth, you find air and sometimes water. What I like is the next slide is, okay, how do you form oceans and mountains from this? Boom. You have the external crust is unstable and dried by the sun. It cracks and collapses, causing water expulsion from the earth interior to form oceans, owing to a primordial catastrophe. Here are the first mountains. The oceans is the water that is expelled out. I think it's lovely. You know, you don't want to do any anachronism with what they had at that time in terms of knowledge. This is fantastic in terms of creativity, right? Not saying that it's the way it works now we understand in the way we understand it now, but in terms of mind step, that's very very impressive. Descartes never went to the field. This was a philosopher. This guy was doing thinking. I think, so I am. This is Descartes. Huh? So he was not doing field geology, and actually the geology was, or these models relied on common sense knowledge at the time. So geology started just before with stratigraphy, with the work of Tectonics, Danish. And imagine by looking at such the final state with observations, you probably recognize here discordance, structures. So imagine a model whereby sediments would deposit on top of each other, would be eroded from underneath, the caves, collapse, and then another series of deposits, then erosion underneath, collapse, and this is the repetition of discordances, unconformities. Another Earth model that came after the discovery of gravity, the gravity field by Newton, the one of Buffon. Earth gravity tells us that the Earth interior is not made of a fire. It's full of dense material. So there's no such thing as a fire. The Earth's round shape probably is a result of crystallization from a molten body, which gives it the shape of a drop. And mountains, well, in that time frame, in that mindset, might come from after crystallization of the primitive rocks from the molten body. As the Earth was cooling, it might have been shrinking, and with this shrinking, we might explain oceans and mountains. Again, that's marvelous. With the understanding that he had, it's marvelous. You know, I introduce more things based on more knowledge than the previous model. But again, Buffon was universalist. He was doing interdisciplinary science, biology, geology, and all sorts of things. It was too much for him to grasp everything. And in particular, geology was not very developed at the time. And it started to really develop when people started to do geological maps and cross-sections. And that started also in Saxony, in Bavaria, in Germany, nowadays Germany, with the first delimitation between different units, maps. And then the understanding of the relationship that you see on the surface is provided by cross-sections. If you want to do tectonics, structural analysis, tectonics, geodynamics, you need to do maps, cross-sections, I think. It's very important. Not only very detailed analysis of samples, put them into a context. From that analysis, they identify primary rocks, crystalline, without fossils, then secondary rocks, stratified, some derived from primary rocks by erosion, and some rich in fossils. And surface deposits, non-consolidated. So you can see here the beginning of the Earth scale stratigraphy. And this fed the thought of Werner. Actually, no, I need really here to apologize. My understanding of history of science and geology is mostly relying on Westerner world, because that's where I'm coming from. So if you guys have information about what Indians were thinking about these topics, I'm really curious to learn about it. I started to read about history of science at a larger scale than just history of Western science, but I don't find many reference to that. No, I'm really curious, about how Asians would think about it, how Africans thought about it, South Americans, North Americans, before Western world discovered it. So Werner, so I have to apologize. Do you have any knowledge about history of science from India? Some? No? I'll be really curious. If you guys can send me references, I'm happy to read it. So Werner, he built on the maps and cross-sections of Saxony, and he defined primitive rocks, granite, gneiss, schists, precipitated in primordial ocean before the formation of continents. And his idea was that all rocks formed by crystallization of minerals in the Earth's ocean, mostly water. So, and the time is going like this, linear progression of time, and irreversible processes. Primitive rocks, transition rocks, endured carbonates and detrital rocks, correlated at the Earth scale. That's very important. That's really the outcome of his work. Secondary stratified rocks, and tertiary alluvial rocks. Well, this has to be cancelled. That's from French. That's a relic from French. Alluvial, which is alluvial. And really the outcome is that he identified what we call the stratigraphic time scale that is still efficient today, used today. Primitive rocks, secondary rocks, tertiary rocks. Archean, Proterozoic, Paleozoic, Mesozoic, Cenozoic. We just changed the names, but the observation was there. And then he had to do some adjustment in his theory that with volcanic rocks. Especially in Saxony, you have these columns, basaltic columns, and they couldn't ignore that there was some volcanic rocks, and volcanic rocks didn't form by crystallization of minerals in an ocean. And magmas, you can see them put and placed at the Earth's surface today. So he put that at the end of his work. Magma erupted from volcanoes, but that was not in the original work. So his mindset was so strong that he managed almost all his life not to incorporate volcanic rocks in his model. So in other words, when you're going to move forward, you don't want to be too strong-minded. You need to incorporate things that even are not fitting your model. At the time, there was a debate with Plutonism and uniformatism that introduced the rock cycle. Hutton is often cited, quoted as being the one that is responsible for that. If you read Hutton's book, it's very difficult to understand. It's written something totally different from what the style we have now. Anyhow, he identified clearly the unconformities, developed on that after the work of Tectonics. And you see here rocks that are banded with folds, metamorphic rocks, schists, separated by a layer of soil from sediments that are unconformably overlying the metamorphic rocks. So he identified that these rocks were former sediments that transformed into rocks owing to heat and pressure, metamorphism. Rocks then uplifted to the surface and then are transformed by weathering and erosion to sediments. And this introduces the rock cycle, up and down, up and down. The first trip to the Alps, well, mountains were sort of left on the side because it was difficult to climb on mountains, you know, at the time. And look at how these guys went with sticks, you know, carrying a lot of material, almost like they were almost going like we are with the clothes we are wearing here today, right? So imagine the challenge to go up on the mountain that is not the Everest, but it's still almost 5,000 meters high, with a lot of glacier. And this guy, de Saussure, he sort of put a challenge to the people of Chamonix in the Alps and say, okay, I'm going to give some good reward to the first one who's going to find the path to the Alps, to the top of the Mont Blanc. And this guy was a geologist. You see his hammer, a compass, and then all sorts of material to measure pressure, temperature, and humidity. You know, he was doing a lot of things. And among the things that he discovered was from the foothills of the Alps, folded limestone. What can you tell about folded limestone? What is the message?
That it used to be a marine area. It used to be part of ocean.
Yeah. And you here, so go and continue, follow up on that.
He got subducted with another plate after collision, and as a result, it was subducted.
Yeah, so you have some knowledge in there, because you take anybody and show the fold limestone, say, okay, that's a rock, you know? But you have knowledge. You have knowledge that this is marine rock, deposited at the horizontal. And it's folded now, so it means that it's been deformed. So what I want to get you there is that you put your knowledge in order to build a model. This knowledge allows you to elaborate an initial state that you compare in your mind with the final state. And us as scientists, we need to, if we want to test the robustness of our models, to really rebuild all these stages between our knowledge and the final state, which is what everybody is seeing out of this room. What is our input? So structural geology of crystalline rocks continued. This guy is named Durocher. In French, is from the rock. So he had the right name to do it. So he identified folds, different type of schistosities that are folded several times, budines, and that's all from the Armorican Massif in France, Western France. Cornwall in southern England was also a big place for development of geology. They identified the relationship between bedding and cleavage, granitic veins, intrusive into metamorphic rocks. We'll come back to that tomorrow morning. And this was also a place where there was big exploration for ore deposits, coal at first, but also iron, and that participated in the development of the industrial revolution. And that's not it's not by chance that these years are connected with the Industrial Revolution and geology development. This also brought people to look into the rocks, and I was surprised to discover to realize that the first goal to look at rocks under a microscope was to find water. They were not looking at minerals at first, they were looking for water, because they wanted to test this hypothesis of Werner and Hutton, if rocks are all coming from water. So, they found water inclusions. Werner is right. It's all coming from water deposition in water. We have different interpretations now, but the observation is there. And then I look at textures. On here, garnet andalusite schist in the Alps, granite, magmatic textures, metamorphic textures. And that came with the development of technology, of microscope technology. So it's also, our understanding, knowledge is also tied up with technological improvement. LA-ICP-MS. With LA-ICP-MS, you can go one step further in terms of the precision of analysis. Contact metamorphism, so that's moving next step, is to try to integrate. I don't have the time here. I mean, I'm not sure how I'm doing, so I don't know when I started. 10:30? Okay. Okay, I'll move a bit. So then try to understand now what these textures and minerals meant. And at first was contact metamorphism, what that was identified in the Vosges mountains, at the border between France and Germany, with cross sections. That's the road. So that's outcrop description, cross sections, and mineral description with textures. We would call now these textures porphyroclasts, porphyroblasts. So this was identified at the time with here internal structures in the minerals, and the same was shown here as minerals in an aureole around granite. That's a granite. This is metamorphic rocks, and here there's an aureole with andalusite that was overgrowing the previous structure, and they interpreted that as contact metamorphism. And everything was set to build that very nice schematic representation of relative chronology by Lyell in his book of 1857. There are some things that are not possible here. I give that, maybe Malika will give that as an exam to students. And I would say for first year students, you take only this part and try to identify all the events by order. But for more advanced, try to sort out this part. And probably I found it paradoxical. There are some things that are not geologically possible with our understanding. So either he made a mistake, or we don't know enough to understand that. Regional metamorphism was another way to explain metamorphic minerals by Barrow in Scotland, where he identified different zones marked by the presence of different minerals: sillimanite, kyanite, garnet, biotite, chlorite. And he identified or defined the metamorphic isogrades with their relationship with structures, folded bedding and cleavage. And this now fed the first maps, large-scale maps, in northern France and southern England, with the mineralogical map first, so the presence or absence of minerals. And you start to see here geological units. That's France. And here myself, as I know geology of France quite well, I recognize the Variscan Massif, the Paris Basin, the Aquitaine Basins, the Pyrenees, the Alps. Everything starts to show up on this map. And that started from minerals and then rocks. The first geological map at the scale of a continent or part of the continent is the one of Eastern North America by McClure in 1809. Short after came the one of England, 1815. And that's where most of the stratigraphy of the Paleozoic has been built up. And you see also the use of chronostratigraphy with fossils that were recognized to be symptomatic of different sediments, and the nice cross-sections showing the relationship between all these rocks. The one of France came about 30 years after. and they used that stratigraphic scheme provided by Werner with the transition, Jurassic, Cretaceous, Tertiary was all identified at the time. Also cross-cutting relationship between sediments, or the basement, folded sediments, stratified sediments and veins, cross-cutting them. And this served to build a cross-section at the scale of the Pyrenees. So that's where I come from. No, Toulouse is somewhere here. And this is remarkable. You see here the Miocene, so that's a cross-section like here. So you see the Miocene unconfirmably overlying the Mesozoic, that is overlying the Paleozoic, and in the center you have the gneisses of the internal massif that are exhumed. After the map of France came the map of Germany, and you start here to have a way to build the map of Europe with a consistency in colors. And this color scheme is the one that is still in use in most maps. So that's also something I want to insist in. No, I'm not sure if there are geophysicists or geochemists in the room, but no, Malika says, so I can speak freely. I hate the maps where the colors are just jumping to each other. I know, if we have a common language, it's a common color scheme. If you use colors that are nice to you but are not understandable to each other, to other people, that is, we need to speak the same language. So if I see green, I know it's Cretaceous. If I see purple and pink, I know it's metamorphic gneisses from the basement. It comes right away to my brain. Geological map of India. I didn't find the author other than the geological survey, but it was done in 1877, so you recognize the Deccan Traps, most of the Archean Proterozoic basement, the Himalayas. It's kind of nice. The high Himalayas were difficult to reach, obviously. And from that time, it was also the time of well-scaled geological maps with the same scheme. And that's remarkable. To do that type of synthesis is remarkable. You can identify the Archean Proterozoic cratons, the different orogenic belts, Urals, the Variscan, the Alps, the Cordilleras, everything is there. And that fed thoughts about regional scale geologic tectonics thinking, with here the work of an Austrian, Suess, that identified the different tectonic belts. The oldest one is the Caledonides, that affects basement that is before the Carboniferous. And then what he called the Altides, that continues in Asia, and that's what we call now the Variscan. And then the Altides posthumes, which are the Alps. And he thought that these were close to each other in terms of timing, and they almost follow each other right away. The work of a French guy, Marcel Bertrand, who also went to North America and identified there was a continuity of these belts across the Atlantic, which was not obvious, to try to find. So he called the Hercynian and Caledonide belt, find their traces in the North America. So now, how these data fed models for mountain formation? Well, at first, after the ones I showed you before, the collapse of a dried crust and the shrinking of the Earth, it was thought that maybe magmatic processes would come into play with the build-up of mountain belts, and it's taken here from Fombourg, a German guy, that looked at the chaîne des Puys in central France and saw that each of these mountains was a volcano. So he thought maybe that's the process that builds mountains. This idea was sort of developed by Scrope, that here related the exhumation of plutonic rocks, gneisses and granites in the central part of mountain belts to the formation, the rise of uplift of the surface and glide of cover rocks, sedimentary rocks that form folds in the foreland. So here the folds are not related to, in this model, not related to horizontal shortening, neither to convergence. And we'll come to that later on, define all these very, but the idea was also very, very interesting, that you have a uplift here and then glide of units from the central part to the outside. Earth cooling, shrinking was modeled with a inflatable balloon. He tried, sort of, Dobre drew some lines on it and looked at what happens when the balloon deflates. And this fed the idea that earth cooling and shrinking could lead to pentagonal mountain system, wide pentagonal and not hexagonal or strange. But Elie de Beaumont, who was one of the guys that did the French map, geological map, thought, okay, maybe pentagonal. So he drew great circles on the sphere, and he thought they could match the different belts he had mapped in Corsica, Sardinia, Western Alps, and Central Alps. Where you see here all the unconformity between the tertiary rocks, secondary rocks, primitive rocks. Experimental deformation also allowed to reproduce structures observed in rocks, and that gave the idea that here we can monitor the amount of shortening. So that gave the idea of balancing cross-sections from sediments. Try to retrieve their original state before deformation, and then evaluate the amount of shortening. Another type of model that was very popular in the early 20th century is the geosynclines. It was identified that rocks were deformed specifically in zones with a belt-like shape. That Seuss has also identified that. And the idea was that maybe that was not related to shrinking, but maybe to the weight of the sediments that would cause sinking and subsidence, and then shortening. Well, this is the cause and effect is sort of included in the cause is included in the effect. This implies that the trough, the space for the sediment deposition, is created by the sediment. So it's kind of a paradoxical relationship. The sediment says, I want to deposit here, so I'm going to create my space. It's kind of a logical problem, I think. You need to have space that is created before the deposition of the sediments. I think it makes more sense. Anyway, that was also a way to explain the zonation of different belts. In terms of Earth internal structure, so geophysics, gravimetry, seismology, allowed to have a first idea of the Earth interior, and comparing these signals with meteorites, allowed to build another more refined Earth model with the identification of that there is a dense nucleus made of nickel and iron. And that's basically based on the identification of the iron meteorites that have the right density and the right behavior in terms of seismic wave propagation to be in the Earth interior. And then a mantle made of silica magnesium, the CIMA, and the CIAL, the crust made of silica and aluminum, mostly. And that brings us back to continental drift, which was built mostly on geological evidence from the continents. The oceans were almost unknown at the time. So you had geologists were much in favor of that, based on sedimentary rocks and fossils correlation across continents, crystalline rocks, glacial deposit structures across continents. See here a reconstruction with also the cratons and the Archean cratons nucleus and the Proterozoic belts across the Atlantic and the fit between the coast of South America and Africa, West Africa. So geologists were much in favor of that, and also the need to find ways to explain the large horizontal motion. And this was also nourished by the identification of metamorphic nappes, which also led to the zonation of mountain belts, and here the example of the Variscan belt with a foreland made of sediments, a zone of intermediate Reno-Hercynian and Saxo-Thuringian made of deformed Mesozoic, and not Mesozoic, deformed sedimentary rocks, and then the internal zone, called here the Moldanubian, made of metamorphic rocks and plutonic rocks. And as these were identified to be, for example here, the Moldanubian internal rocks were identified to be overlying the Saxo-Thuringian rocks in the external zone, that led to the idea that there was a need for large horizontal displacement. And these guys were in favor of continental drift. Argan, who also was a supporter of continental drift, in order to explain the formation of the Alps between moving continents, but also the Variscan belt, that's just along the same trend as the Alpine belt. And he was getting crazy here. No, I'm not. We just take a minute to read that. The strong axial exaltation was marked in the Hercynian times in what was to be the Massif Central of France. It seems that no fact is sufficiently disturbing to prevent us from tasting on those rafts where our destinies float, the delight of the wise outburst to which Mr. Wegener invites us. We're not writing science like this anymore, right? But it was inspiring, I think. So I'll leave you to that now, before a short break. Geologists, most of them, were in support of continental drift, but geophysicists said, okay, okay, but maybe we need motion, but it doesn't work. The Cial is on top of the Cima, and the Cima is the strongest Earth shell. So how come the Cial could deform the Cima so easily and move on top of it, like if it was floating on top of water? Be careful, I'm going to trick you on that today, at the end of the morning. You're ready? So the guy, Jeffrey, an English geophysicist, says there's no way. And the force you are invoking, Earth rotation and the centrifugal force, the Coriolis force, is not enough to move such big bodies. What is strange? So we need a driving force for continental drift. What is strange is at the time of continental drift by Wegener, 1912 is the first version, 1929 the last one. Well, the lithosphere had already been described. Barrel, 1914, is the first one who talks about a lithosphere based on the isostatic rebound of the Scandinavian continent after melting of the ice cap there. And he measured the rebound by measuring displacement of hooks for boats. They were identified on the coast of Norway, the Drakas from the Vikings, and you could find hooks very high on the coastline. So it allowed to measure uplift of the coastline through time. Amazing, huh? So in this way, he measured the elastic rebound of the lithosphere. He identified that there is some kind of a strong layer, the lithosphere, sphere made of stone, compared to a much weaker one underneath that is allowing for this rebound. The geodetic evidence of isostasy points towards the existence of a thick and somewhat plastic zone beneath the more rigid lithosphere. So Wegener didn't use that, and that's too bad for him, because he had everything at the time. But we'll see in the next hour how we can use that to link with mountain belt formation. So if you have any questions, thanks for some of you participating, but you also can ask questions if there are things that are not clear or inspiring you. Yeah?
In this figure, was this M and N?
M, N, I'm not sure. You can find these papers fairly easily. Barrel, lithosphere, you can find the papers and all the mathematical development of that on the internet.
Sorry if I missed something or not. So in this figure, so are they just showing lithosphere as a part of continent only here?
Yeah. Other?
Lithosphere and astrosphere only as a part of continent here? Or
Yes. Yeah, M and N might be different continents. That's possible, but I'm not sure. Maybe there are different, laterally different type of continents, and that might be the. It might be somehow illustrating here the Scandinavian relative to the Atlantic. I'm not sure. That's what is your question, huh? Maybe that's relative motion between different part of continents or Earth's surface, I would say. On other slides? Okay, let me just ask you if, because I know the public is very heterogeneous. Okay, who is a PhD student here? Or maybe PhD, a faculty member, okay, one, recognize the older guy. And the other ones are bachelors, first year, second year, third year, third year, masters, sorry, masters, third year bachelors, second year. Is it first year also? First year? Is it okay? I mean, for you, yeah? No, so. Because it was difficult for me to adjust the presentation to this very large audience, from first year to faculties. So I hope everybody is going to get a grasp on or take something out of it. And this was the easiest part, the history, right? So then it's going to be a bit more challenging. So do not hesitate to ask questions and stop me if there are terms that I use that are not understood. Okay, so we'll take a short break. Is it okay, Malika? Good timing?